if you absolutely said no, we wouldn't do it.
That's fine. It's a good idea.
Good afternoon. Welcome. Happy to see everybody here today for our latest installment in our research series. And today we have Catherine Schaefer with us from Carilion Clinic. Catherine joined Carilion Clinic about 11 years ago, she was telling me. And so she has a long-term investment in the system's success, right? I was teasing her before. I said, you have a very tough job today. You have to make statistics interesting. If anybody's up to it, Catherine. Catherine has a very applied background. Her master's degree is in human development, and her bachelor's work was in the field of psychology. So she's not really a mathematician as much as she is an applied researcher. So I think we're blessed to have her as part of our team. Catherine, we really appreciate your time today. Welcome. Thank you.
Thank you. Thank you. I'm happy to be here. It's been a while, and as I was going over my PowerPoint to get ready, I'll tell you up front, I always face a little bit of a struggle with, well, this got expanded to 2 parts, but how do you cover statistics in 2 hours? And really, how do you meet the needs of everyone? Because everybody has very different needs that are usually specific to their particular project or area. And so just to start off, I know this may not cover everything for everybody. It may be a review of things you already know. It might be some stuff you're not as familiar with. But if nothing else, after today, you'll know who I am and where to find me if you need help. And that's as much, in some ways, the goal as anything. So let's go ahead and get started. The objectives for today, you'll see, are to be able to distinguish among some different statistical applications, to also start to get an idea of what statistical technique might fit with a particular research question that you may have in mind. Actually, out of curiosity, how many of you are currently working on something in the research or QA/QI realm? Okay, most people don't come to this if they're not, so that makes sense. And then finally, to get an idea of the database structure that is helpful. If you're collecting your own data, it's not so much of an issue with a retrospective study, but if you're collecting your own data, there are some things that can be done to just be efficient and save me a little bit of work on the front end in terms of how that database is set up. So we'll see some examples of that and touch on those topics as we go along. So why do we have to care about this? I know you guys all probably do something that's much more interesting to you with 95% of your job than statistics. So why are we here? Why do we need to pay some attention to this? Well, obviously, it lends credibility to any research that you do. No one's gonna, or most journals that you might be looking to publish in are going to expect a certain level of statistical rigor, and so that has the practical effect of helping you get published, and also just makes those results credible. That's the numbers and the hard data that back up whatever conclusions you're making with your paper or your study. And then even for people who, and so since pretty much everybody put their hand up when I asked if you were working on research, this doesn't apply as much, but it also makes you a better consumer of other people's research if you have a basic understanding of statistics. And this is really important, I think, for all clinicians as we have moved and I guess continue to move further into evidence-based practice and all the other ways that healthcare has changed. Even really just in the time I've been at Carilion, I've been able to observe the shift. And so if you may come across a journal article and ask yourself, or somebody else may ask you, do I want to change what I'm doing, or should we as a department change what we're doing based on what's been published in this paper? And if you have at least kind of a basic grasp of statistics, that will help you figure out if you should go with what they're asserting in their article. You can kind of use that knowledge to pick holes if there are any to be picked, or satisfy yourself that the study was done well and that it might be worth incorporating their findings into your clinical practice. So there are two categories of statistics, descriptive and inferential, and that's kind of the big umbrella for what we'll be talking about today. And we'll start by talking about descriptive statistics. Every study that you ever conduct will involve descriptive statistics in some way. It may stop there. That may be all that you do. Especially some QA/QI projects that I work with are mostly just to describe what's going on. Let's collect some data and see, I kind of call it the what, when, where, how, those kinds of questions. Let's just get a snapshot of what's going on in a particular department, or with a particular patient population or whatever. So descriptive statistics are used to summarize a set of data, and the ones on the slide are some of the more common ones. So of course, N is your sample size. The mean, the median, and mode are measures of central tendency that kind of tell you generally what are my data doing. The mean you're probably the most familiar with, is just the average. The median is the 50th percentile. It's the point at which half of the values are higher and the other half are lower. And that can be a very useful statistic to use when our data are skewed, and we'll talk about that a few slides from now. And then the mode is not very commonly used, but it describes the most frequently occurring value in a set of data. So if you have 5 kids and their ages are 2, 3, 3, 4, and 5, your mode would be 3, because you had 2 kids who were 3 and the other ones were all some other value. So the most frequently occurring value. So that kind of describes, on average, in general, what do the data look like. But then we need to know something about the variability of the data. And the standard deviation is a pretty common measure of that, as well as the 25th and 75th percentiles. So the reason this is important is, and I'm resisting the urge to go draw on the paper, but I think maybe I can do it without it. So if you imagine, let's just stick with age, because that's an easily accessible example. But if you imagine a group of patients, and their average age, their mean age, is 40. That's information, obviously, but what you don't know is, are most of the people right around 40? Are they 30, 35, 45, 50? Are they all kind of right there in that same age range? Or do they go from 10 to 80 and have a big spread? And so that's why you really need the central tendency, the mean, and that variability together to get a good picture of what's going on in the data. The 25th and 75th percentiles are just useful in the same kind of way. We'll talk about those more in a minute, as well as the minimum and maximum, which are what they sound like, just the lowest value, the highest value, and again tells you something about the spread of the data. Frequencies are something that I run every time data come into my hands. I'm going to give you back the frequencies. They're actually very useful for catching typos and data entry errors. They are basically just the count of the number of people with a particular value. So again, with age, how many people were age 20, 21, 22, whatever all the values are, and how many people had those values. And then from that, you get percentages that can be useful to describe your data set. So this is just kind of an example summary table for with some made up LDL data. Pretty much all the data I have here is made up, so don't take anything away from the content of the numbers in that way. Again, we have this tells us we have 150 patients in our sample, and their average LDL was 140.8 with a standard deviation of about 20. Again, resisting the urge to draw bell curves and things on the paper, but we'll see how that goes. I don't want to use too much time.
Feel free to draw.
So then the lowest value that anyone had was 98. And then skipping over, you can see the highest was 195. The middle point, the median, was 143, and then Q1 is the first quartile, the 25th percentile. So that's Q1, and then Q3 is the 75th percentile, or the third quartile. So this is just a typical kind of descriptive table that you might get if I were working on your data, this would be something that you would see, or something that you might run yourself. Scatter plot is also a really useful visual technique. So I said descriptive statistics were part of every study that you'll ever do. If you stop there, that has a place, but they're often useful just to get to know, you've planned your study, you've gone out, collected the data, and then you really, before you get too far into your analysis, you want to have a good understanding of who do we have here? What do we have? What are the data telling us? What kind of form a picture in your mind of what your data set looks like. So visual techniques like a scatter plot are really helpful. And you can see here on the x-axis we have minutes of exercise ranging from 0 up to 200. So that might be like weekly exercise, I guess. Hopefully, right? Not monthly or anything. And then on the y-axis we have LDL cholesterol, and again, made up data. But each of these little points is just one person's value, one person's combination of values, their minutes of exercise and their LDL. And so then you can start to see what kind of a pattern or trend or relationship is showing up here between exercise and LDL. So we would say, actually this is how you know this is made up, because you usually don't get anything that looks quite this pretty. Frank is shaking his head. But this is very linear, which suggests something going on there that you would want to look into further. If all of this plot space were just kind of randomly full of dots all over, you would think, there's probably not a whole lot going on. And that's informative too. If you really think something should be going on, then that might mean you have, again, data entry errors or something strange going on with your data, or you just might find out that it's not looking like there's a connection between two things. So a scatter plot is a really useful tool. Wait, did I skip something? Okay. Then another, I don't use these very much, but it's kind of good to know what they are. A box and whisker plot is just another way of describing some of these things we already talked about. And this is a busy slide, but what you're seeing here is, so basically these are all of the numbers in kind of table form, and then these are box plots over time. So what you have below are the different days, and you're seeing how each day compared to the others and kind of forming a trend. This line connects the means of each day. This is diastolic blood pressure over time. So you can see the trend over time, and you can see what was going on descriptively in each day. In a box plot, the line through the, let's pick one where they're not in the same place. So like in the second one from the left, the line across the box represents the median. It's the 50th percentile. And then this, is that a plus sign? Whatever this symbol is, I think it's a plus, is the mean. And so it helps you to see visually if the mean and median are similar. And then this point of the box is the 25th percentile. This is the 75th. and then you get to the minimum, the maximum. You can represent outliers, really far out data points on a box and whisker plot. Again, just another kind of visual way of representing your data. Then a histogram is also useful, especially for figuring out what the shape of your distribution is. So who remembers learning about bell curves somewhere along the way? Most people kind of think that's what statistics is about a lot of times, which it is. That's a very important piece. And so histograms are useful. I use them a lot, actually, because a lot of our data here are not shaped in that bell curve. They're not normally distributed. So I'm often running these to figure out what the shape of a distribution is. And I think, yeah, so now we'll kind of pull all of this together and talk about a normal distribution versus a skewed distribution. So, all right. In a So this is approximately what a normal distribution would look like. And when the data are normally distributed, this point through here represents the mean, the median. And you can see why it's the median, right? Because 50% are over here and 50% are over here. And then it also represents the mode because it's the highest point on the curve, so it's the most frequently occurring value. So this is kind of the defining property of a normal distribution. And the reason this is important is that a lot of our statistical tests rely on an assumption that the variables fit this pattern. So that's why we care about that. Unfortunately, it can sometimes cause frustration, so I'll go ahead and say unfortunately. Some of the data that we work with that people commonly like to study are not and will never be normally distributed. And length of stay is the best example of that. This is, and I guess to kind of emphasize it here as I talk. So I'm going to exaggerate it a little bit, but what we end up with length of stay is something kind of like this. And I'll expand what's on the slide to say that we go from 0 days or a portion, a decimal point after that, to, I mean, you can probably tell me better than I can tell you. I know we have some patients who are here 6 months. So you might have out to 180 days. There aren't very many of them, but there are some that are here that long. Even though most people go home, I guess it's around 4 days or whatever. So what this means is that the statistical techniques we use for a variable like length of stay have to be different. And that's why we have to look at all of these things. That's why it's one of the reasons I run descriptive statistics at the beginning, is just to get a sense of, okay, which situation are we working with, and how does that inform the analyses that I'm going to do down the road. So that's kind of a good segue into inferential statistics. And as it says here, when you're doing inferential statistics, you're using data in a sample that you probably are the one who defined the sample, to hopefully make inferences or draw conclusions about the population. So the first thing I would say is don't think about that as the population like the global population, because it depends on what you're studying. You may be studying the population of pediatric blood cancer patients. And that is a population in itself. There's still no way you can go all over the world and round up all of those people and put them in your study. So you have to take a sample. But the population is as you define it. So there are times that I run into people here at Carilion who are studying something, and they're really interested in something that's going on within Carilion. And in that case, that becomes their population, which changes the rules of things a little bit, because then you're really not doing statistics anymore. Inferential statistics are on a sample so that you can conclude something about the population. If you happen to be studying the whole population, some of the things that apply with statistics, inferential statistics, no longer apply. That's not something you would have to remember or figure out yourself. That's what the biostatisticians are for. So there are two types of inferential statistics: estimation and hypothesis testing. And estimation is the kind of question that asks, maybe what is the rate of a particular complication associated with a procedure? It tends to be, you're not asking a question about, is this different from that? It's more like, out of this group of patients, how often does something happen? What proportion of patients experience this? And it's usually associated with confidence intervals. So the answer might be something like, the complication rate was 1.2%, and then you might see a confidence interval around that that tells you how good our estimate is. If we came up with 1.2%, how likely is that to be true of the population? I don't do as much of that kind of thing as I do the hypothesis testing, and that's probably, if you've had a statistics class in the past, that might have been more what was focused on, was the hypothesis testing. So that's your more typical question of, I want to know if this group is different from this group in a statistically significant way, and that usually uses p-values to make that determination. So that's kind of the difference in those two things. Are there any questions about those two, or the difference, before we go on? Yes?
Questions, can I make a comment?
Sure.
So if you talk about inferential statistics, I'm sitting here thinking about how a lot of people in this room are involved in testing people's knowledge about a given subject, like through written questions or exams.
Mm-hmm.
The logic is basically the same. If you want to know what somebody knows about the management of diabetes, you can't obviously ask them every question there is about management of diabetes. You have to take a sample.
Right.
And the same logic applies. You're sampling that universe and inferring what they know about that based on how they do on that subset or your sample of questions.
Right.
It's the same kind of logic.
Right, and you have some of the same measurement issues, I guess, in terms of if they didn't get a lot of sleep the night before, or the coffee pot wouldn't work that morning, or whatever other thing, similar to some of the issues that come into constructing a sample for a research study, because, and we don't have time to really go into that here, but there are things you can do to make the quality of your sample better or worse in how you design your study. So yeah, that's a good point. It is kind of like assessment in that way. So there are a few things that we want to talk about regarding data before we jump into the actual statistical methods, because you can't figure out what statistical technique is appropriate until you understand what type of data you're working with. So categorical data is one sort of major type, and those are data that I would describe as being labels rather than numbers. So, and within categorical data there are two kinds, nominal and ordinal. So let's take, for example, eye color. That's a good example. That would be nominal because there's no ordering to eye color. Blue, brown, green, gray, hazel, whatever. There's no inherent ordering to that. Gender is the same way. There's no ordering to that. It's just, they're just categories to represent different things. With ordinal data, so this is still categorical, but there is some order to it, a natural order to it, such as a pain scale that goes from none all the way up to severe or very severe. So obviously there's those categories represent an increase in pain, but there's no mathematical relationship that defines. You can't say that moderate pain is twice as much as no pain. There's no mathematical relationship between the categories. Then under continuous data, I sort of would break that out into two categories where discrete, or what you could also consider interval data, are best thought of probably as count data. So it's numeric data, but there are specific values and there aren't values in between. So the number of cars in a parking lot, that's discrete interval data, because there can't be a half of a car, hopefully. You would be counting a whole car. There either is a car or isn't in a parking space. And the example here, the number of patients, trauma patients or any other type, admitted on a given day, things that are basically counts are going to be discrete data. Then kind of the last level is most, I guess, truly continuous or numeric, where the data can take on potentially an infinite number of values. So pretty much all lab values fall into this definition, because however many decimal places you want to take something out to, it's there. Weight, blood pressure, height, all those things can take any value that is possible, basically, and is not limited to a discrete count. So then we can figure out what type of data we have in terms of categorical versus continuous, but we also need to think about two kinds of variables in our study: our dependent variable and our independent variable. So our dependent variable is kind of the outcome variable. It's the thing that we think is going to be modified by whatever treatment or whatever we're implementing, if we're doing something in the study, or whatever characteristic that the patients may just bring to the study themselves, that will affect an outcome, and that's your dependent variable. It could be something you're trying to predict. So let's see, I have an example coming up later that looks at patients in two different weight groups, based on their body weight, and then the time to a therapeutic dose of a drug. So in that case, the time to the therapeutic dose would be the dependent variable. That's the outcome variable. It's the thing you're interested in. The independent variable is whatever it is you think is influencing that outcome. So again, that may be a characteristic like gender or weight or whatever. It may be something that you're not manipulating, or depending on what type of study you're doing, it could be, if you're assigning people to a control group and a treatment group, then their group membership would be the independent variable, and whatever you're doing to them in the treatment group versus the control group. So it's whatever you think is going to influence your outcome. So once we know and can identify the type of data we have in the independent variable and the dependent variable, then we can get a guess about what kind of statistical tests we may be using, because they don't all work for all types of data and all combinations. So this graphic kind of shows you just an idea. I mean, it's not exhaustive by any means, but just an idea of, if you have a categorical independent variable and you have a categorical dependent variable, you're probably going to be looking at a chi-square type of a situation. Whereas if you have a categorical independent variable but a continuous dependent variable, then you're going to be doing something like a t-test. So a t-test comparing the means of two groups, which we'll talk about in a little bit. So this may be helpful if you're trying to figure out what statistics are appropriate for your situation, but I should also warn you that this is not exhaustive by any means, so don't panic or worry if this makes no sense or doesn't seem to fit your situation. This is a simplification, but kind of could put you on the right path for figuring out statistical analysis. So at this point, we're going to kind of shift gears and talk more in detail about a few different statistical techniques. And we will get through, in these kind of example scenarios, we will get through t-tests, and then you'll have to come back. I'm not even sure when my part 2 is.
September 8th.
September 8th? Okay, you'll have to come back in September to find out about the other techniques that we don't have time to get to today. But so please, as we get into this, if you have questions, comments, anything, feel free to ask or speak up or whatever. That's totally fine. So this, we'll start, there are actually 3 different kinds of t-tests, and we'll start with the one sample t-test, which is actually, I'm not sure if I've ever done one in my 11 years here, but you never know, there might be a time when it's called for. It is used when you have a sample and you want to see how that sample compares to kind of a known norm or a known group. So the example here is, we know the statewide average ISS for patients that are in a motorcycle accident and admitted to the hospital is 10. So then we ask, does the ISS score of our patients here differ from that statewide average? So that's a kind of scenario where a one sample t-test might be an appropriate thing to use. So this is our first chance to really see kind of a little snapshot of what your data might look like. And I may take, because I think I must have talked really fast through the first half hour, so I'm going to take a little more time now to talk about this. Most people that are collecting data on their own, so I would say, first of all, it kind of falls into 2 camps. People who are getting pretty much all of their data out of Epic and probably don't ever have to deal with that themselves. If everything's already in the medical record, it comes to me directly from the people who access it, and you as the researcher don't really have to do anything. Sometimes it might be a hybrid where you get some information from Epic, but you have other things that you may need to do chart review for, or whatever, if you're using a questionnaire or something, and then you kind of have to tack those 2 things together. Or it may be that you're collecting all the data on your own. So I guess those are the 3 most common scenarios or ways that I end up receiving data from people. Excel is still the most common thing that people seem to feel the most comfortable with. I would say, I think actually that's about all I really ever get is an Excel file, which is fine, that's great. I use SAS primarily for my statistical software. I'm familiar, I know how to use SPSS, but we've chosen to use SAS instead. I have the same, well, actually I may have more access to SPSS than some of you, I'm not sure. But I do have it if it's something that you use or you're familiar with, or you want to, if you want to ask a question about it, or you want to work in that and do some of it yourself or whatever, that is an option. But SAS is what I use most of the time, and it reads Excel files pretty well. There are some places where they don't always get along, but I've been doing this long enough that I've encountered most of those, except when the versions change, sometimes new things crop up. But for the most part, I've kind of figured out what needs to happen for SAS to read an Excel file smoothly and correctly, and to kind of get that process started. So even just as an example, you'll see up here that there are no spaces in my variable names, just because sometimes, and I don't always keep up with if SAS can accept spaces or not, but it definitely did not in the past. So I just am in the habit of using underscores to separate, if I need to have multiple words in my variable name, I tie everything together with an underscore. I try not to make them too long. I think the limits on name length have gone up over the years, but again, kind of keeping things short. And so that's this is pretty typical to have the data set up this way. Most of the time what people are collecting is going to be in a format where each row, and of course most people don't send me a 2-column spreadsheet, but so you imagine other columns extending out this way, but each row is going to be a unique patient, and then the columns are the variables of representing the different data that you've collected. I'll just tell you as an aside, it's easiest for me if it all goes in one tab. Sometimes people, and I always feel really bad, sometimes people have obviously spent a lot of time, they put a lot of pretty colors and fonts and bold and borders and things, and they divide things up into a lot of tabs, but in the end I just need it all in one place, and I actually don't care what color it is. And again, because we have a little time, just to talk about, you might have some different subgroups of patients that you want to identify. Maybe, I'm not sure I can make up any on the fly that relate to this example, but if you had, well, even if you had them by years, let's say, and so you decided, I'm going to put all the 2012 patients in one tab, and then I'm going to make another tab for the 2013 patients and another tab for the 2014 patients. The way my mind, or the way a statistician, data person's mind would work about that would be to say, just make a column that says year and put the year in it and put them all together in one sheet. So there are a lot of little issues like that add up and can cut down on the time on the front end as far as data cleaning and getting everything kind of in shape and reading it into SAS. And so I like to sort of pass those things on as much as possible. And I will do, obviously I do whatever needs to be done to get things ready to go. But even I'm happy to help people set their Excel sheet up ahead of time. And then that way we kind of all know what we're doing before you start putting numbers in there. And that works well. So those are just some of the things to think about as it relates to the format or the structure of your database or spreadsheet. So anyway, now that you've had a long time to look at this, we just have a patient ID here and their ISS score here. And so then, and you don't have to remember this. Now, if I were teaching statistics like at Jefferson College, I would make you do this by hand, and I would be unpopular with you for it, but I won't make you do that here, and you don't have to remember this. But what basically is happening is the numerator of this formula is the difference between the mean of our sample here and the statewide mean. And then this numerator is divided by, this is basically representing the variability. And we don't have to go into that any more than that. But this is how you get the t-value, which is the test test statistic. And then, in order to figure out if that's significant or not, what you're looking at is what's the probability that this value of t was by chance or is due to something, a variable. And that's where our p-value comes in. So this 0.05, which is still pretty much a commonly accepted p-value, and I won't, they're over, gosh, as far back as when I was an undergraduate, and beyond, way beyond that. There's always been debate, I think, about p-values and should we use them and what should it be and is this really the right way to do it. But I think in spite of that debate, we still pretty much, this is still pretty much what we do in terms of figuring out statistical significance. So a way to think about what that means, if we did this t-test and our ISS was statistically significantly different from the statewide average with a p-value of less than 0.05, what that means is 5 times out of 100 or less, whatever it is, we would get that result due to chance. But the other 95 times, it's a real finding. It's due to a variable. Something about our motorcycle accidents down here are different than everybody else's in the state. And so finding this 5 times out of 100 due to chance is kind of like saying we're okay with being wrong 5 times out of 100. If we say this is a real result, 5 times out of 100 we would be wrong, but we're okay with that. That's what that 0.05 means. Sometimes you want to be even more sure, and so you might use 0.01 as your p-value, as your cutoff, and then you're saying 1 time out of 100 I would find this by chance, but the other 99 times it would be a real thing, and I need that level of, you know, I want to be that much more sure about whatever it is I'm saying, because maybe it's more important to your patients or whatever. So that's kind of how to think about statistical significance. And this is an important note here, that if you don't find a statistically significant difference when you expected to find one, that doesn't mean that there's not a difference. It means that you didn't find enough evidence in your study to be indicative of a difference. But it doesn't mean, oh, there's no difference. It could be something about your sample, because again, your sample is only a small piece of the larger population usually. And so you just don't want to conclude that there's no difference. You may need, if it's an important topic or you have reason to believe that it's something to continue looking at, you may need to repeat the study and you might find something different another time around. So that's just kind of an important side note. So that's how a 1-sample t-test works. The logic for a 2-sample t-test is not much different. And this is a more common, I do these fairly often. This is still a pretty common technique here, and it's also good because it works well with smaller samples. Around 30 or so is, well, 30 to 50-ish. You don't really need a lot more than that in each group to get to have enough power in your study, and we won't talk about that today. I think that's in part 2. It works well for small samples, and so you're comparing the means of 2 different groups. So this is the example I referred to earlier. Is there a difference in the time to therapeutic threshold of a drug in lower weight patients compared to higher weight patients? This actually is a real study that I worked on with a pharmacy resident this past year. The data are made up, though, to illustrate a point. This would be their group membership, and I mean they would have a patient ID and all of that other stuff, but I left it off the slide so we could see better. this shows, if they're in the lower weight group versus the higher weight group, and then their time to therapeutic threshold in hours is in this column here. And just looking at these numbers, what do you think would be the result of a t-test here? Do you think the groups are different? They probably are. It's always, I always hesitate to say anything conclusive without doing the math. But yeah, because it looks like the lower weight group is taking less time than the higher weight group. So the test statistic is a little more complicated looking for a 2-sample t-test, but still the same principle where the difference of the means is in the numerator and the variability is in the denominator. And the process is the same. You have your t-value and your p-value, and you determine if it is statistically significant at that 0.05 level. Then the last kind of t-test that we'll talk about is the paired t-test. And this is used when you have data from the same patient at 2 different times. So I should have said before, in the 2-sample t-test, the people who are in one group can't be in the other group. It has to be 2. That's why it's also called an independent samples t-test, because there can be no overlap of people in terms of their group membership. But then when you have a situation where you have data on people at multiple time points, such as a pre and post, then you use a paired t-test, which takes into account the fact that my score on a test is going to be, if I take a pre-test and then I do something and then I take a post-test, my scores are going to be more like themselves than my scores and your scores, because we're different people and so the math behind the paired t-test takes that into account, and that's why it's important to use it if you have data on someone at multiple time points or at 2 time points. So you're comparing pre and post, and I don't have a elaborate example for this, but just imagine some kind of a 10-point scale, what's your satisfaction with your job or something like that. And these are their scores at the pre point in time, and then this is patient 1's score at pre and then at post. And so you're comparing pre and post for each subject. Again, similar formula, similar process, and you determine if there is a significant difference from pre to post. Typically if whatever you did with them in the interim, you're hoping to see an effect of that. So if, if I take a job satisfaction survey and then maybe I attend some training or something, some HR training, and then I take the same survey, it has to be the same measure afterwards, and then we see what was the difference, and hopefully that can be attributed to the training that took place in the middle. Now it might be attributed to other things, but that's all part of study design and planning a good study. So that's how a paired t-test works. And then in part 2, we'll get to kind of a lot wider variety of statistical techniques. We'll talk about analysis of variance, or ANOVA as it's commonly called, and then correlation and regression. Regression is growing in popularity here at Carilion. More and more people are coming to me with issues and questions that fit a regression sort of a structure. So we'll talk about that, and then also we'll talk about categorical data and proportions. That's a pretty common thing I see a lot of as well. And then we'll talk about power analysis. So there's a lot in part 2. Today was kind of almost laying the groundwork for some of those things, but these things are probably more where the rubber meets the road in terms of what I see people doing on a regular basis. So also, just to kind of let you know, what we do. There's myself and one other full-time biostatistician who are here in Roanoke. And then we have a third person who works flex time off-site. And so the three of us are pretty much it for, especially for research type purposes. We have some other people who work on other types of projects, like more business related and metrics types of things, but the biostatisticians are who you would contact for research or usually for QA/QI types of needs. And so we like to get involved early on if we can, because we can help you with study design and look at a lot of things up front that can affect how everything goes from there on. It's always unfortunate when somebody comes to us and says, hey, here's a lot of data I collected, can you analyze it? And it's the first time we've ever seen them. Sometimes there are things that, and then you want to say, well, if I just wish I had had a chance to talk to you, however far back in the future, to kind of help you iron out some wrinkles that might make things go more smoothly. So we do like to get involved as early as we can. We do a lot of power analysis for people, so basically helping them figure out how many patients or subjects they need in their study to kind of give it validity, just for the sake of, that's a good, I guess, good enough word, kind of so that you can find what you're looking for. That's a sort of easy explanation of what statistical power is about. So you want to make sure you have a big enough sample, but obviously not so big that it becomes your life's work and you don't ever get to do anything else. So finding that number is an important thing that we do a good bit of. And then helping to figure out, sometimes data sources, and with data collection, forms or spreadsheets, and then of course doing the analysis and then interpreting the results, and even helping to write a methods section or results section of papers, posters, whatever, because we, that's definitely something we're happy to do, to take what we've done and put it in that language that is needed for putting it out in the public. Our contact information is there, but we are, obviously in, I still want to say group-wise. I'm really aging myself by saying that. I guess in Outlook, all of that is there. There is, I'll just tell you, there's another Catherine Shaver that works here with the same spelling and everything. Her middle initial is B and mine is H. So if you don't know that, and she pops up first because of the B, she's nice enough to send me my email, but that is just, I should have put that there, but anyhow, just look for Catherine H. Shaver if you're trying to get a hold of me. And I guess I'll leave that up there. And so we don't have a lot of time, but are there questions or comments? Yes.
That's actually great. I think it's helpful. Can we get a copy of the PowerPoint, or can we get like a one-page quick cheat sheet?
Yeah, I would be happy to, and I don't know if there's Sandy, I don't know if you send those out, but I personally would be happy to send them out. I was just trying to not kill lots of trees by bringing tons of copies, but yes, I would be.
I posted a PowerPoint with the video on our website, Continuing Professional Development.
Okay. Yeah, and if you have questions about things, we definitely are, even if you don't have a project or need data analyzed or anything like that, just feel free to contact us. I've had people contact me, I was reading this article and it says this and I wasn't sure what that meant, can you help? And we're happy to do that. That's what we're here for.
We'll be back on September the 8th, part 2. Plug that into your calendar now. You don't want to miss it. This was an excellent overview. Thank you very much.
Thank you.